Hello there, guys. Today we're going to be doing paper one of the November 22 examination session for chemistry. Not too bad of a paper, so let's just dive right in. So, question one: how many oxygen atoms are present in 0.05 moles of hydrated barium hydroxide? So, first of all, let's convert this into scientific notation to make it easier to do calculations with. And then we'll look at this oxygen atoms, which means that you need to calculate how many oxygen atoms are present in 1 mole of barium hydroxide. So in one molecule, let's just count 2 and 8. So total is 10 per molecule. So now let's calculate how much will be per mole. So that's 10 times 6.02 into 10 power 23, which is 6.02 into 10 power 24 per mole. So now let's see what happens when we turn this into the amount that we have, which is 5 to the power minus 2. For our quantity, we just multiply the number of moles by 10 to the power minus 2 That's that's kind of really which is an it are not right. Part, uh, again, so So what you see here is to form methane CH4 in the end, you have to get this CH4 in the last equation to the other side. So make this plus 891. That's the first thing you have to do. So you can automatically eliminate these two because these have minus 891. So it's either this one or this one. So now let's look at this. You have a carbon dioxide on the left hand side, carbon dioxide here on the right hand side, which means they will cancel each other out. Because once you write this equation backwards, you get CO2 plus 2H2O gives CH4 plus 2O2. So this carbon dioxide will cancel out. Perfect. Now, what else is left? You have an oxygen here that cancels out. Not both of them, only one. And now you have a carbon on this side, which you do need. So we can leave that there. So let's look at our water. We have two molecules of water on the left hand side, which means that we need to multiply this by 2. So 2 times minus 286. And that'll give you a full oxygen here, and that'll cut out the rest of this oxygen, and that'll make this 2H2, which is exactly what we need right here. So perfectly perfect. You end up with C plus 2H2 gives CH4. Done. So you need to multiply the second one by minus 286 and 891. So option D is the correct answer. Let's go ahead to question number 15. Which magnitudes of lattice enthalpy and hydration enthalpy would result in the most exothermic enthalpy of solution? So let's go ahead and draw out what that means. So if this is your base value and this is your full, these are your gaseous ions. From here to here, you have delta H lat. This is your lattice enthalpy. And from here to here, this is your solution. Yes, this is your solution, delta H sol. This one right here is your delta H hydration. So to try to make this as small as possible to make it the most exothermic, we are going to make this magnitude of lattice enthalpy super small so that this distance right here is not that high. Now, to make sure this is even smaller, let's make the magnitude of hydration enthalpy large. So maybe it's even like this, where you literally have a tiny gap, or maybe it's even like this, where this is your lattice enthalpy and this is your hydration enthalpy, and you have an exothermic delta H sol. So that's the kind of technique you have to apply here. A little bit of thinking, but option C is your correct answer. Let's move on to question number 16. Which alkene has the lowest standard entropy? So entropy is defined as the amount of chaos that a particular atom has. We know that solids have less entropy than liquids than gas, and heavier molecules have greater than lighter molecules. So let's look at the heaviest molecule, and that's going to be this one. But that has the highest standard entropy. When we're looking for the lowest, we have A. So option A is the answer. Question number 17. At which temperature could delta H, delta S, and delta G all be positive? So let's write out the equation. Delta G is equal to delta H minus T delta S. So when you need delta G to be positive, that means that T delta S must be less than delta H. And for this, we will just assume delta H is positive for whatever reaction we're taking, and delta S is also positive, which means that T must be very low in order to ensure that T delta S is not greater than delta H, which would make this negative. So moving on to question 17b. So 18, sorry. What initial rate of reaction can be determined from the graph? So let's go ahead and look at this. This is concentration in moles per decimeter cube, and this is time in seconds. If you guys remember, the unit for rate of reaction is moles decimeter cube second inverse. Moles per decimeter cube per second inverse. This means that if you find the slope of this graph, excuse my terrible graph drawing skills, this digital is kind of weird. But in the actual paper, this should very much be possible. So going and drawing a tangent line to it, you find that this would be your rise by run, and you can find the slope of this tangent. So I'm going to do you a favor and skip that. You get 0.2 and 2 seconds, which is 0.1 moles, oops, mole per decimeter cube per second. Option A. Question number 19. Which changes would increase the rate of an exothermic reaction? So when we're talking about the rate, we're not talking about equilibrium here, guys. Keep your reaction separate. This is a very common point of confusion. Equilibrium, rate, mixing them up, you make mistakes in the paper. Keep them separate. The rate is always proportional to increases in temperature. So increase the temperature and you will increase the rate. Next, decreasing particle size increases the surface area, which means that you increase your rate. So question number 19, option A. Let's go ahead to question number 20. The data is given for this following reaction. So this is an example of how you find the rate from a given rate table. So rate is equal to K times concentration of X power something times concentration of Y power something. Finding those somethings is the important part here. Let's go ahead and see this. Look at this. When the concentration of X is doubled, but the concentration of Y remains the same, the rate multiplies by 4, which means that you have a second order, which means that the reaction is second order with respect to X. Next, when you increase the rate, when you increase the concentration of Y by 2, but keep the concentration of X the same, the rate stays the same, which means that you have a zero order reaction with respect to Y. So looking at which option matches this, we see x squared, x squared, x squared. This is incorrect, but we have y power 1 here, y power 0 here. That's the answer you're looking for. This is incorrect and this is incorrect. Question number 20, option C. The activation energy of a reaction with the rate constant K and the temperature T. So this is where you need your Arrhenius equation. K is equal to AE power minus EA by RT. This means that when you take the natural logarithm on both sides, ln K is equal to ln A minus EA by RT by your logarithmic properties. And when you kind of analog that to your y is equal to mx plus c, you find m, the slope, is equal to, well, produces a straight line. You find m is equal to minus EA by RT by R, and c is equal to ln A. This means that y is ln K and temperature is 1 by temperature. That gives you 21, option D. Question number 22. For this particular reaction, what is the value of Kc, the equilibrium constant? So Kc is given by product, power its coefficient, by reactants, powered their respective coefficients. So these are all formulas you need to remember in order to be able to solve a paper. So let's just plug it in. 2 power 2 by Cl, which is 0.2 whole cubed times 0.2, which gives you 2 squared. So let's convert this into 2 into 10 power minus 1. So 2 power 4 into 10 power minus 4. Because these two are the same, we can write it as 0.2 power 4, which is 2 into 10 power minus 1 whole power 4, which gives you this. So we can cancel this, 1 by 4 into 10 power 4. And that is where you get 0.25 times 10 power 4, 2500. So quick maths in order to be able to solve questions quickly in your actual paper. I'm taking extra long to make sure I explain each of these questions correctly. If you have any questions, please do leave them in the comments below and I'll try to get back to you as soon as I can. Looking at question number 23, which of these changes shifts the equilibrium to the right? When we look at this, shifting it to the right requires an increase in concentration on the left-hand side, a decrease in concentration on the right-hand side, or if you were to given the delta H value, increases or decreases in temperature, respectively. Here, since we are not given the delta H value, let's go ahead and look at this. Addition of 0.01 molar HCl. This is a very dilute solution, so it wouldn't particularly increase the Cl minus concentration that much. So we can ignore this. Part 2, addition of concentrated hydrochloric acid. This would increase the value of Cl minus because the dissociation equation for hydrogen chloride or hydrochloric acid is H plus Cl minus, and this Cl minus is directly used here. Next, you have the evaporation of water, and you have 6H2O here, which would decrease the concentration on the right hand side, driving the equation to the right. This gives you options 2 and 3 only. Up next, question number 24. When equal volumes of a weak acid and a strong acid are titrated with the same base, what is the same? Let's look at this. The initial pH is going to be different because this means that the solution in the burette is your NaOH and your conical flask is your acid. So the initial pH of this is going to be different because a weak acid is going to have a higher pH than a strong acid. So this is incorrect. This would be different for both of them. Heat evolved in the neutralization. This is also incorrect because a strong acid is going to evolve more than a weak acid. And looking at question C, looking at option C, volume of NaOH for complete neutralization is going to be the same. Now you might be thinking, oh wait, what about the dissociation? That's taken into account because as you keep neutralizing pieces of your weak acid, you continuously regenerate the weak acid, which means that the volume of NaOH for the complete neutralization of both acids, strong and weak, will be the exact same because the concentration of H plus ions at the end of the day, when you add up the fluctuations in the weak acid caused by dissociation, will be the same as the strong acid. And of course, electrical conductivity will be different because the weak acid does not have the same number of ions as a strong acid. So a strong acid is going to have better electrical conductivity in Siemens per meter than your weak acid. So 24th, option C. Question number 25. Which species has the weakest conjugate base? And when you have a weak conjugate base, you have a strong acid. So let's just go ahead and look at this. This is a neutral substance, so that's out. H2CO3 minus is a base actually, so it has a conjugate acid. So that's even worse. Nope. This is an acid, but it's a very weak one, and you form NH3, which is a strong base. So this is also out. HCl, as you all know, is a strong acid and gives you the weakest conjugate base, Cl minus. Let's look at this. Which two solutions will form a buffer when mixed together? Conditions for a buffer is a strong acid plus a weak base, or vice versa, of course, weak acid and a strong base. And additionally, you need 2 times the whatever is weak in comparison to strong. So if you were to check this out, HCl, NaOH, absolutely not. The rest of these are weak acids, strong base. So let's go ahead and look at this. 50 centimeter cube, 50 centimeter cube? No, those are equimolar. That's incorrect. 50 centimeter cube, 100 centimeter cube. That looks right. Let's check out a fourth option. 100 centimeter cube. Oops, watch out for which is which. There's half the amount of weak acid as strong base, which means that your base is greater than your acid, which means that the strong one is greater than the weak one, which means that this is incorrect. However, this one, your weak is greater than strong, which means that 26th is D. Question number 27. Which species can act as both a Lewis acid and a Lewis base? So when you think about this, a Lewis acid is something that accepts a pair of electrons, and a Lewis base, which is a nucleophile, donates electrons. NH4 plus is only an acid, and since it accepts electrons and it donates H plus. Cu2 plus is also an acid because it accepts electrons. And CH4 is also incorrect since it cannot accept because it is in a very stable configuration. So your answer is A, because it can donate a pair of electrons and at the same time it can accept a pair of electrons, forming other species. Up next, what occurs during the operation of a Voltaic cell based on the given reaction? Chromium plus Fe2 plus forms chromium 3 plus and FeS. So this means that this is the anode because you are forming ions, and this is the cathode because reduction is occurring. So this means that electrons are moving from chromium to iron because its electrons are moving away from chromium to form this ion 3 plus towards iron so it can form its actual metal. So Cr to Fe, that is correct. And let's look at this, the ion movement in solution. Ions are moving towards Fe2 plus to regenerate or to be reduced at the cathode. So this is correct. And Cr3 plus are also moving away from Cr. But the only you need to make sure that both values in the table match, which means that question number 28, option B is the correct answer. Question number 29, what is the coefficient for H plus when the reaction equation below is balanced? So let's go ahead and split this up as per standard redox balancing procedures. So first let's take up elements. So this is our oxidation half equation. And let's go ahead and balance this out. So you need to just add 2 electrons on this side to balance the charge because there's no oxygen, no hydrogen, nothing. So this is fine. Next, let's go ahead and balance out our NO3 minus. NO3 minus and NO. You have a deficiency of oxygen on this side, 2 oxygens, so 2 H2O, and now you have an excess of 4 hydrogens on this side, on the right hand side. So you add 4H plus here. Now the charges are imbalanced. So you add an extra 3 electrons on this side to make both sides neutral. Now you need to multiply this by 3 and this by 2 in order to cancel out the electrons on both sides, giving you a final answer of 3, 2, 8, 3, 2, and 4. Yes. And the coefficient for H plus when the equation below is balanced, 29, option D. Question number 30, standard electrode potentials for half cells involving chromium are shown. So which statement is incorrect? So for this part, you got to remember that the higher the reduction potential, the greater the tendency to be reduced, and it will oxidize lower potentials. This means that chromium can oxidize, chromium 3 plus can oxidize chromium because this is greater than this. So, but it cannot oxidize this because it is lower. Oh, sorry, I mixed that up. This is greater than this, so it can oxidize it, but this, but minus 0.47 is greater than 0.74. So it cannot oxidize Cr2 plus. Option B is the correct answer for question number 30. Question number 31. Which factors affect the amount in mole of the product formed during electrolysis? So let's go ahead and think about this. In electrolysis, electrons are added to a particular ion, let's say Cu2 plus in this case, forming the metal Cu. So obviously you see here that the number of electrons that have to be added to the compound, to the ion, defines the amount of compound that will be formed. So 2 moles of electrons are required to form 1 mole of copper. This means that the charge on the ion definitely affects it, since electrons with Cu plus 1, um, you only need 1 mole of electrons. Therefore, the charge on the ion definitely affects the amount of product formed. Next, the molar mass of the ion. This would generally affect the mass of the product, but here we're looking at the amount, not mass. As such, this does not affect the amount in mole formed during electrolysis. Finally, the duration of the electrolysis. For this, we're going to write out a simple formula. I is equal to Q by T, which means that charge is equal to current times time. This is a formula that you'd be well used to if you're a physics student, but otherwise, this is pretty straightforward. This means that the greater the amount of time, the more charge that's added, therefore the more number of electrons, which means the greater amount of product that's formed. So question number 31, options 1 and 3. Moving on to question number 32. Which are isomers of C5H12, also known as pentane? So pentane, let's draw the skeletal structure of pentane. 1, 2, 3, 4, 5. This is the skeletal structure of pentane. So let's just go ahead and compare these. This is clearly wrong because this has 1, 2, 3, 4, 5, 6 carbon atoms. So for this question, you will need to know how to read your skeletal structures. So make sure you have that down well in organic chemistry. So option 3 is incorrect. Let's count on option 2. 1, 2, 3, 4, 5. 5 carbons. 1, 2, 3, 4, 5. 5 carbons. So question number 32, option A. Moving on to question number 33. Moving on to question number 33. Moving on to question number 33. Which compound has a chiral carbon? So this one, if you've been doing a lot of questions, you'd know that 2-bromobutane is the correct answer, since it has a chiral carbon on carbon number 2. But let's just talk about what a chiral carbon is. It needs to be connected to 4 different functional groups. This means that if you look at bromoethane, which has a CH2 and a Br connected to it, this is incorrect because it's connected to a CH3 on one, and H is the same on the first carbon. So that's incorrect. On the second one, 2-bromopropane means that the bromine is in the center. So it's like this. And again, it's connected to 2 of the same functional groups, CH3. Therefore, that's also incorrect. Finally, bromopentane, we see that 3-bromopentane is a symmetrical molecule, which means once again, it is not a chiral carbon. Therefore, for question number 33, option C is the correct answer. Moving on to question number 34. Which conditions best favor oxidation of primary alcohols directly to carboxylic acids? This means that you are going to undergo oxidation, which means you need excess acidified potassium dichromate, so not few drops, and you will have to reflux it. Distillation will produce an aldehyde. So 34 is B. Which statement best describes retrosynthesis? Looking at this is incorrect. Let's just go through each and every option. The reaction conditions needed to convert the product of the reaction back to starting materials. Incorrect. This is essentially making the products from the This is essentially making the reactants from the products. Next, synthesizing a target molecule by working back from the target molecule to the starting materials. This is correct. Retro in this sense means working backwards, not going back in time like this traditional methods. And this favors the equilibrium, not necessarily. So option B is the correct answer for this one. Moving on to question number 36. Which combination of reactants will convert nitrobenzene to phenylamine? This is a reduction, and that means you need tin and hydrochloric acid, not acidified potassium dichromate, which is an oxidizing agent. Now, here's the part that many students forget. There is a second reactant involved in the conversion of nitrobenzene to phenylamine. So let's draw the entire reaction. Starting with benzene, adding your nitrating mixture, which is HNO3 and H2SO4, forming phenylamine. Now, the mechanism of this should be known to all HL students. So, yes. Next, we're going to reduce this with concentrated tin and HCl, forming forming an intermediate NH4. So this NH4 is actually positively charged, so that means it's unstable. Now, upon the addition of a base OH minus, it grabs this extra hydrogen and converts it to phenylamine. Yes, converts it to phenylamine, NH3. So therefore, your second reagent is this OH minus. Option A is the correct answer. Up next, we have question number 37. A well-tested scientific idea, which has been used to make predictions, cannot explain a particular event. Which statement describes the scientific approach to this dilemma? Scientific idea means that it is a theory, not a hypothesis. Next, when you have something that's well tested and it's been used to make prediction, but it cannot explain a single particular event, that means it should be revised, not discarded, because it still applies to many rules of the system. Up next, question number 38. What information about 2-hydroxybutanoic acid can be inferred through the various spectroscopic techniques? Mass spectroscopy, infrared spectroscopy, and HNMR microscopy. HNMR spectroscopy, sorry. So let's go ahead. Mass spectrometry immediately means that you find the molar mass of the compound. Next, IR gives you the types of bonds in the group, which means this. Finally, HNMR gives the positioning and the number of hydrogen environments in a particular compound. So that means option A is the correct answer for question number 38. Question number 39. What information can be deduced about a compound through X-ray crystallography? X-ray crystallography gives you bond angles and bond lengths. So if you think about something like the structure of DNA that was found through X-ray crystallography, this is for those bio students that are watching this video right now. You know that the structure of DNA was found by Rosalind Franklin, and how her experiments deduced the bond angles and bond lengths of DNA. It does not give you boiling and melting points, nor does it give you bonds that will break during fragmentation. This is mass spectroscopy. So question number 39 is option B. Finally, question number 40. Which compound has the hydrogen environment shown in the HNMR graph? So the easiest way to do this is first identify what you see. You see 3 hydrogen environments. So let's go ahead and draw these out. This gives you CH, double bond O, H. This has only 2 hydrogen environments. Ethanoic acid, CH3, bond C, double bond O, OH. Again, this only has 2 hydrogen environments. Next, methyl ethanoate, CH3, CH3, C double bond O, that does not look like a double bond O, bond CH3. Now let's look at the number of hydrogen environments here. You have 1 caused by this, and the second one is this, caused by this. This means that you have a total of 2 hydrogen environments. let's look at the last option, propanoic acid. CH3, let's draw this out right. CH3 bond CH2 bond C double bond O OH 1 2 3, 3 hydrogen environments. So that means the correct answer to this question is D. So that is the paper, guys. I hope this made sense, and if you have any questions, please leave them in the comments below and I'll be sure to get back to you as soon as possible. Don't forget to subscribe and comment any future papers that you'd like me to do.